Now I would like to introduce our first keynote. It is my pleasure to introduce Budhu Bhaduri, who is a corporate research fellow and the director of science programs and partnerships at Oak Ridge National Laboratory. In this capacity, he provides strategic guidance and leadership to scientific and programmatic endeavors spanning geospatial science, artificial intelligence, machine learning, and scalable, high-performance computing, particularly focusing on the defense and intel programs. Additionally, he fosters strategic partnerships with leading universities, research institutions, private companies, charitable organizations to help expedite the development and implementation of these innovative solutions. He is a fellow of the American Association of Advancement of Science, the American Association of Geographers, and he served on Geographical and Geospatial Sciences Committee of the National Academy of Sciences. He's a founding member of the U.S. Department of Energy's Geospatial Sciences Steering Committee and is a recipient of the department's Outstanding Mentor Award for his dedicated service to the department for developing workforce for the nation. And I do have one interesting fact and connection back to St. Louis for Budhu. His first ever geospatial panel to participate on was actually in 2001 at the ASPRS annual conference called Gateway to the New Millennium that was hosted right here in St. Louis, Missouri at the America Center. So please help me welcome to the stage Dr. Budhu Bhaduri. Welcome.
Thank you, Tara, for the wonderful introduction, and good morning, everybody. It's always an excitement to be in this building. As Tara said, that my first ever national panel on geospatial was in this building, and I wanted to share something special about it. The day before I was traveling to St. Louis, I was incredibly nervous because I was a young researcher, and I realized that I was on a panel with luminaries in the field, and it was about evaluating the first inauguration of the USGS national map. So there were stalwarts in the field in the room, and the day before my watch broke, and I was incredibly nervous, and I told my wife that I'm not sure, how embarrassing it's going to be if I ran over. And she, with all the wisdom of graduate degree holder in English, told me that don't be nervous. The moment you realize that you have run out of English, that's 9 minutes. So quit at that point, okay? So I've kept that always in mind. So this morning, what I'm going to do is I will give you a glimpse of our journey, my personal journey with high-performance computing at Oak Ridge National Laboratory. Now, there is a very large community, international community, that is dedicated towards this science. But I thought that what I would do is give you a very quick introduction to who we are at Oak Ridge, talk about how HPC evolution has happened and the impacts it's making on the GEOINT mission, and what can we expect going forward. And then hopefully we'll have some time for some QA. So Oak Ridge is one of 17 national laboratories as part of the U.S. Department of Energy. We are the largest science and energy lab among the 17 national labs. And we have one of our identities is stewarding the leadership computing capabilities for the nation, for the world. So this is one of my favorite things to talk about. When I first arrived at Oak Ridge, across from my office in a big room was this high-performance computer called Intel Paragon 150. So all the climate scientists in DOE had concluded that if there was a 150 gigaflop machine, the climate problem could be addressed adequately. So this machine was built with 150 gigaflops. And one of the colleagues I had the fortunate experience of overlapping with, Yang Cheng, he ran an algorithm to me that was the first ever example of how a large machine was being used in geospatial science, was an aerial collection of imagery over the Oak Ridge Reservation. And you can see the seam lines showing up because the aircraft comes back at a different time over these. And so Yang did a color balancing algorithm and ran it on that big machine. And if you kind of look at it, you can see that now the seams are kind of fading into a more uniform. So this was back in 1998. It's pretty amazing. So I witnessed the evolution of a revolution of high-performance computing in the nation. It came out of a congressional act. And Oak Ridge, over the last 20 years, have fielded what we call serial number 1 machines, which has been the largest machines in the world till. And it is pretty amazing that the first exascale machine, which is Frontier, that does amazing level of calculations. My favorite anecdote is that if every person in the world did one simple, what they call floating point operation, one simple calculation every second, the amount of calculation the entire population of the world will do in 4 years, Frontier can do that in 1 second. Okay? So that's the scale of computing and power. I wanted to point out 3 different timelines in this massive journey. Okay? One is in 2007, we published the first paper, and I had the opportunity to present it at IGARS in Barcelona that talked about that. It was the only paper across the world that talked about using high-performance computing for processing satellite imagery. That was 2007. 2010 is my first presentation on can large computers handle data processing challenges. And I made a presentation to the community, and where we said that it will take about 30 years to process the entire land site archive for detecting urban areas. 30 years it's going to take. So just so you know that between 2007 and 2010, all the supercomputers combined, their processing capability, storage, and everything else matches the iPhone that you and I are carrying today. Okay? It is pretty amazing that how far we have come. 2023 is, I would say, another landmark, is when we actually fielded supercomputer in partnership with NGA, which is called Freya. It sits at Oak Ridge. It's about a 2 petaflop machine. That means it can do 10 to the power 15 calculations per second. And I want you to keep that in mind as we go forward, because I will be pointing to Freya as the yardstick. So how are we applying HPC today, or why is HPC even important for us to consider? So HPC and AI are almost 2 sides of the coin. Okay? The incredible investments that have gone into HPC have led to AI, and what became the field of GeoAI, or Geospatial Artificial Intelligence, is essentially fueled by the enormous amount of data sets that the community has collected over a period of time. Very few other scientific community had this kind of data sets to work with. So it was a fertile ground for advancing AI, and the entire global community has been doing that. But what we're really chasing is that, can we do this fast enough? Okay? We knew that scaling image analysis on a large cluster is possible, but can you reduce that latency from data to decisions? How fast can you go and process data sets? So the next few slides, I'm going to draw your attention to the fact that how in different areas of geospatial intelligence we are employing HPC and what are the gains that we are seeing. Now, it is not a completely solved problem. We are still working on it, but we have come a long way, and the potentials are really, really great. So my colleague, David Page, he's leading this high-resolution terrain data project in collaboration with NGA. For those of you who have been around this community know that SRTM, the NASA's Shuttle Radar Topography Mission, it took almost a decade to create a global terrain data set. But with fortuitous stereo pairs and at HPC that is tailored to do that kind of processing with GPUs, that's what the Freya cluster was originally created for. And today, Dave and his team with his NGA colleagues, they can process entire state of Alaska in about 24 hours. And every 3 months, the whole global terrain data at 1 to 2 meter resolution can be brought up. So I like the way Dave talks about it, saying, we don't need to do change detection. We can just, process the whole data again because it's that fast and that's efficient. It's like you don't really want to fix a TV when it's cheaper to just buy a new one, okay? So it is pretty amazing. Here is another example of HPC being used. Matt McCarthy, who is also here, Matt's been looking at, can you create high-resolution bathymetry data using the same imagery that we have collected for the government. So this is commercial worldview data, and then also map water at very, very high resolution over the things, right? So if you take Frontier, and you take one node of Frontier, Frontier has about 9,000 nodes, which have these GPUs and CPU clusters. The performance right now is about 140 square kilometers per minute, okay? So what that means is that if you take Freya, the machine, the 2 petaflop machine, in about 4 hours, we can process 2 kilometer width swath along the entire global coastline and produce bathymetry data. Similarly, if you take CONUS and take about 40 nodes out of the 9,000 nodes in Frontier, you can map every water body in less than 24 hours. Lexi Yang is leading a collaboration with Dr. Don King at NGA on reducing the latency of gravitational anomaly data over the world. This is a convolutional neural network that has been scaled. So this model originally trained on a very large computer called Summit, which was the one before we had Frontier, and then now runs on smaller clusters. But this has brought down the generation of data from about 5 to 8 years to less than a year for a global scale data set at ArcMinute. So it's amazing progress in there as well. One of my favorite examples is, can we find all the settlements in the world? This was a goal many years back. Titan, which used to be the large machine before 2 generations back. So the experiment there was that if we took enough data sets and can we scale it to a machine that is as large as Titan? And at that point, Titan was the largest machine in the world. So we put about 45 terabytes of data, which is about close to 2 million square kilometers of data, and mapped every settlement in Yemen in about 1 hour and 41 minutes using the entire 5,000 or so nodes that were in Titan. Now, I want to remind you one thing, that Titan today is one rack of Frontier. One of these cabinets in Frontier is equivalent to this one big machine that's sat on the floor. So building detection with HPC has not just has gone a long way from just being detection over to delineation. Okay? So this is an example of Dr. Dalton Lunga and his AI team at Oak Ridge. They're leading this work on foundational AI model that now generates these polygons that are delineated buildings and not just detected buildings, and without a human being intervening. So in the early days, we would detect buildings, and then there would be human interventions to make the edges straight, to make it look like what we call the regularization process, and make it look like buildings. Today, AI with HPC is producing outputs like this without any humans touching the data in between, which is pretty significantly amazing. Similarly, on the analysis side and operational side, we are using a very similar approach, using these kind of building detection technologies to understand building damage. And Dalton and his team are doing this at pretty unprecedented speed. In a matter of minutes, we can now not only tell how much the damage is, but different categories of damage and report the number of buildings in a very quantified way. And I'm going to skip over these because, if you are interested in any of these, we welcome your comments and interactions. We are going to be here. Come to the Oak Ridge booth, and we can take you deep into any of these examples. One of the things that I think is very promising is how do you use HPC to create very smart models and then deploy them at the edge or in the operational area. So this is a work that Andrew Duncan, who leads our EOS team, Autonomous Systems team, he's doing with Department of Energy, specifically Emergency Support Function 12, is to understand, can we automatically detect utility poles that are damaged? So this model was actually generated using a very large machine, and then now installed on a drone on an NVIDIA chip. And this drone is operationally now deployed, and it automatically detects like a traffic sign pattern about whether a pole is still intact or has fallen and how it's moving along, and then puts that data back to the responders so they can start the restoration planning immediately, because there is no way utility workers can get into the area for a physical survey. So where do we go from here? Okay, and I'm going to put some teasers out, and over the next few days we can discuss these in more details. If we are truly after data to decisions, we have been talking about what does a geospatial digital twin look like. Okay, and I acknowledge the brain power of both David Page and my colleague Carter Christopher. We have been asking this question, saying a twin must have a twinning rate. So how fast can you update the data sets that define your twin? So the examples that I showed you makes us to believe that we are approaching that area where we could be setting up workflows which will allow us to monitor the planet in 4 dimensions in unprecedented speed and accuracy and efficiency. And then build the AI smartness into the system that allows us to then automatically detect changes, monitor landscapes, monitor features. So without HPC, we will not get to this kind of a goal. So over the next years or decades, we will continue to see the impact of HPC on the GEOINT mission. I alluded to a little bit about the foundation models. There is a lot of work going on with large language models that I did not touch, about geospatial reasoning. Can you ask smart questions? I always encourage people to go to ChatGPT and see if ChatGPT's response, if you say that my commute to work is so great that it's downhill both ways. Okay? See if it's what his response is. There is a lot of effort the community is putting in terms of, can you create these kind of large capabilities in a cloud environment? Also, can you miniaturize these kind of capabilities down on the edge, which we call HPC in a box? So we will see a lot of movement there. In terms of processing, I think the 2 most interesting things that the community is looking at is neuromorphic computing which is a lot more efficient in terms of speed and power consumption. And also quantum computing, which is now obviously in everybody's mind, and that, how will we go there? By the way, the next machine that the Department of Energy is going to build in about 3 years is going to be Discovery, which is still going to be a classical computer. But the next one that it will follow Discovery is going to be a hybrid machine with quantum and quantum classical. So we are truly getting closer. The last one is fascinating, which is, can we do faster than real-time simulations? Okay? That's what HPCs are built to do, is how fast can you process these things. So it's not just about can I map, but can I predict the map? And we do it today. Weather is a form of GEOINT, and we are clearly producing anticipatory output from a weather forecast standpoint. So forecasting is anticipation. And we are very good. We are very, very good at weather forecasting. But can you do that similar kinds of things with movements of people, with vehicles, with, can you look at what's happening today or right now and then say, this is how it's going to evolve over the next 10 minutes. So that's what we mean by faster than real time. And it's a lot of anticipation. All right, so with that, I'm going to end here, and we can have some questions.
Especially with a lot of industry out here in the audience today, what is the role of the private sector in high-performance computing, or how do they become involved?
That's a great question. So, high-performance computing is dominated by private sector. If you think about the companies that are out there today, NVIDIA, Cray, it is private sector is our biggest partner with Department of Energy and everywhere else. I mentioned that this is a serial number 1 machine. That means these are unique, very large. But the advantage is that once you build some of these machines and you design some of these architectures, then you get to create smaller instances of those machines and then feed the market that is hungry for it. So that is from a hardware standpoint. Of course, there is the software standpoint is there. The cloud vendors are trying to create capabilities that are in the cloud. What comes hand in hand is the aspect of storage, software, and then use cases. So private sector is an integral part of the HPC world. Without them, it's almost impossible.
Okay, great. And I think they like to hear that too. So, all right. And how does HPC lend itself specifically to the GEOINT mission?
I think HPC, as I was trying to kind of illustrate through my presentation, that HPC will play a few different roles. One is the sheer processing power, right? In the previous panel was talking about as we send these large constellations, how much data we are going to generate. So since 2019, we have been looking at this issue, which we call the trillion pixel challenge. That means if you take the entire world and about 5-meter resolution and you take a picture every day, that's about 510 trillion pixels. So before the next 510 trillion pixels comes, what would you do with, in 24 hours? So without HPC, you just cannot kind of process that data. What I think is more exciting is these sort of edge GEOINT applications, and I talked about the utility pole detection ones, where you are training these models using what we would call HPC, but then you're deploying them on the edge on smaller machines. So that's very very kind of appealing. And then this whole issue of prediction and anticipation is, I think, we have not quite brought that into the GEOINT world as much. I was inspired by the previous panel, and if I can draw on that, it would be great if you could, in near real time or faster than real time, predict the progression of fire. Okay? That's a very, very useful utility app, and I think you will see more and more applications of HPC.
Yeah, like leveraging it, yeah, for those emergencies. Okay, well, great. With this deluge of data, yeah, managing it with those HPCs. Okay. This is something a little bit more specific, again, to the Intel, but how do you manage security in HPC environments with partners? Like, even if it's international or between organizations, like, how do you manage that security?
HPC world brings its own cybersecurity challenges, especially if you have a large machine. There are many components that associated with that machine that you have to ensure that they're all secure. In our intelligence world, we deal with these different levels of users and also different levels of classifications of information. Maintaining those is a great challenge. I think the big machines that I talked about, they're mostly focused on open science. But I would say that one of the research areas that I see coming in the next few years is actually how to manage these multiple levels of security when you have a large cluster that you're trying to share amongst partners.
Okay, all right. And we did get a couple questions in, so I'm going to take one of these. And especially just thinking of it in this environment, where do you think the US stands in HPC relative to the rest of the world?
We are clearly, we have been the pioneer. The US has been the pioneer. Now, just like the space mission, the HPC mission is now becoming global. We know that there are other countries that are clearly making great strides. But it's still, if you look at the AI world today, the AI world is still heavily relying on chips that are made by US companies like NVIDIA, AMD. There are chips that are now being fabricated across the world, especially the other superpowers like China. They are going to be investing in, or they have been investing in their indigenous technologies. But I would say that US is still fairly leading edge in the high-performance computing world. We have been pretty much fielding the largest machines and then putting them to use for different kinds of applications. So the race is, the gap is narrowing. Other countries are, recognizing the opportunity, the investments, and it's getting. But I would say we are still. We would like to maintain this edge.
Okay. Well, we have just barely 1 minute left, so I won't be able to get to all the questions here. But with the student population and a lot of our golden ticket winners, I know you guys had a few winners this year too. What would you tell someone young or new to the industry to how they could become more involved in HPC, or like why they would want to choose that kind of career path?
Oh, that's a great question. I think we cannot have ever enough talent in coming into the world of HPC, especially in the geospatial intelligence world. This is not something that is necessarily part of a standard academic curriculum. So I think it is an exciting area for students to get engaged with. There's going to be a lot of applications. Today's students that are coming out are a lot more well-versed with quantitative computing, AI, and HPC is going to be one of their greatest tools for making an impact for whatever they want to do.
All right. Well, thank you so much, Budhu.
Thank you
again for sharing the stage and for speaking to us today.
Thank you.
Appreciate it.